Welcome back, scholars. In this video, we're going to take a look at an alternate formula for calculating the area of any general triangle using trigonometry. Let's get started. To begin, let's recap what we already know about finding the area of a triangle. We know a triangle is really half a rectangle with the same base and height dimensions, hence the 1/2 base times height formula that you know from back in middle school. This is no doubt a fast and easy way to find a triangle's area, but it depends on you having access to those key dimensions. Remember that a height or altitude must be drawn perpendicular to the side serving as the triangle's base. It's very possible that you don't know the height of a particular triangle and instead know about its side or angles. That's why we're going to derive a new way of determining the area of a triangle using trigonometry. To begin, we'll take general triangle ABC and we'll draw an altitude from the base up through vertex B. This creates segment BD. Next, I'll label that altitude H for height. From here, let's think about some alternate representations of the value H. Can you spot them? Let's start over here with angle A. We could write sine of A equals H over C. Solving for H, we get C times sine of angle A. What about using angle C instead? We could write sine of angle C equals H over A. Again, solving for H, we get A times sine of angle C. If we want to write a relation for the height in terms of sine of angle B, we would instead draw an altitude from vertex A to the side opposite angle A. In summary, we need two sides and their included angle, that means the angle which rests between those two given sides, to find the area of a triangle using the sine formula. Let's try one here. We have 116 degrees and the sides adjacent to this angle to the left and to the right. B and A. We're given that B equals 3 units and A equals 4 units. So we'll take our area formula and substitute the height with 3 times sine 116 degrees. The base will be A in this case. So I've got 1/2 times 3 times 4 times sine 116 degrees. Let's look at one more. We have 3 sides this time, but we'll need one angle. It doesn't actually matter which angle we solve for at this point, so let's just pick angle A. Using law of cosines, I have 4 squared, that's the side opposite the angle we're solving for, angle A. 4 squared equals 10 squared plus 8 squared minus 2 times 10 times 8 times cosine of angle A. Using inverse cosine to solve for angle A, and of course simplifying all the way down, I've got angle A is approximately 22.33 degrees. Now, to find the area, I need to use the sides 10 and 8, the sides which sort of bookend this angle A that I've just solved for. So I've got 1/2 10 times 8 times sine of angle 22.33 degrees. This gives an area of about 15.19 square units. All right, one more thing I'd like to recap, and this comes from way back in your Accelerated Algebra 1 course, and that's angles of elevation and angles of depression. Angles of elevation can be thought of as sort of above the eye line. In other words, take a person and have them gaze horizontally and parallel to the ground outwards. Now, instead, ask them to gaze upwards, just like this. The difference between the horizontal and their actual gaze is referred to as the angle of elevation. This can also be written as the angle of incline or angle of inclination. Similarly, we have an angle of depression. An angle of depression is the same idea. We'll take a person who's looking outwards horizontally, parallel to the ground, and instead ask them to tilt their eyes downward. So their gaze is actually like this, going downward. The difference between the horizontal and their actual gaze, or their eye line, is referred to as the angle of depression. In this particular example, we have a bungee cord fixed to someone's waist belt. The angle of inclination, or angle of incline, is shown here. If you take the point of attachment and then look upward, this 70 degrees represents an angle of incline, or an angle of elevation. Here's another example showing an angle of depression. We have a security camera, which could theoretically be fixed pointing outwards towards the street, parallel to the ground. Instead, as we can see, the security camera is pointing downward, so this represents an angle of depression. That's the difference between pointing the camera outward horizontally and tilting it downward. Now, something else to notice here. Using our alternate interior angles theorem, we can show that the angle of depression is actually congruent to the angle of incline from the ground. If we think of the camera instead as a flashlight producing light, the angle of incidence is equal to the angle of reflection. So in other words, this angle of depression is equal to the alternate interior angle, which is the angle of incline from the ground pointing upward. inside the right triangle. We have yet another example of this where we show that the 23-degree angle is congruent to this angle marked A degrees inside the right triangle. So that's a brief look at an alternate way of finding the area of a triangle using trigonometry, as well as a quick recap from our Accelerated Algebra 1 course on angles of depression and angles of elevation.